All right, I'm going to be working on the backside of your Hess's law note sheet. So we're going to calculate the heat of combustion of palmitic acid. So this is my target equation, and I always like writing this because then I know where I need to go. So for combustion, I'm taking something that has at least hydrogen and carbon, and again, this one has oxygen in it, reacting it with oxygen to form CO2 and water. Okay, and you guys know how to balance equations, so I'm gonna kind of skip over that. Just remember there's 2 here, so that's why it's not 24, it's 23. Solids, gases, for all the rest. Okay. Then the other piece of information is the heat of formation is given. So this would be for the palmitic acid. So this is given, but you have to be able to convert this to an equation. So carbon, they give it as graphite as opposed to diamond, plus hydrogen, plus oxygen in their standard states, which would be gas at room temperatures. And again, this large molecular compound is going to be a solid. So I need to balance this. So I'm going to have 16 carbons, 16 hydrogens, and 1 oxygen, and 124.8 kilojoules. So this is all my known information. So I'm going to use these equations to get to my target equation. So again, it doesn't really matter where you start, but I always kind of start left to right. So I need the palmitic acid as a reactant. So I'm going to reverse this one. So C16H32O2 yields 16 carbons plus 16 hydrogens plus an O2, and because I'm reversing it, I need to change the sign. So I already have one of the pieces that I need for my equation. Now I have to cancel the rest of the stuff that I don't, so there's no graphite in this equation. So I'm going to come back up to my graphite equation, and I'm going to multiply this entire thing by 16. Okay, and I need graphite as a reactant, so I'm going to not flip that. So 16 graphites plus 16 O2s yields 16 CO2s. And then I need to take 16 times this, and that is going to give me negative 6,296.0 kilojoules. Again, when I'm multiplying by a whole number, I'm going to keep that place value. And that's going to cancel my graphites. Now you'll see it's not canceling my hydrogens or oxygens. And I'm not going to deal with oxygen yet. You'll see there's oxygen in the formation of water equation, so I'm going to wait for oxygens. It's like balancing. If it's multiple places, you'll wait till the end to balance the oxygens. Okay. Now I do need to get rid of these hydrogens, so I'm going to come back up to my formation equation for water vapor, and I'm going to multiply again this entire thing times 16. Again, I need hydrogen as a reactant, so it cancels. So 16 H2 gas. Okay, 16 times a half is going to give me 8 O2 gas, yields 16 water molecules. And 16 minus the 241.8 is minus 3,868.8 kilojoules. So this is going to cancel my H2s. Again, I'm looking at what I need. My carbon dioxide I need in my final equation, and my water I need in my final equation. So these all have to stay. So really I need to check oxygen, and if we've done everything correctly, those oxygens are all going to work out. Now, there are 3 different places. So to get my oxygens, I have 16 plus 8 on the reactant side minus 1, which is going to give me my 23 O2s. So the combination of all of these gives me my 23. So that means I'm ready to just combine all of these heats of reaction, and if I put those in the calculator correctly, again, it's going to be addition rule. They're all good to tenths. I'm going to get negative 10,040 0.0 kilojoules for that reaction. All right, question 13, as you can see, has a lot of information. This is based on a real story. So nitric acid on this date was spilled near downtown Denver, Colorado. This spill was neutralized with sodium carbonate, and we want to know the delta H for this reaction. And approximately 2 times 10 to the 4th gallons of nitric acid were spilled. Assume the acid was 70% HNO3 by mass, has a density of 1.42 grams per cubic centimeter. How much sodium carbonate was required for complete neutralization, and how much heat was evolved. Delta H formation for NaNO3 aqueous is minus 467 joules. All the rest are available in Appendix L. So all the rest of the values I'm getting are coming from there. So this one is really not a Hess's law. This is just kind of a summary equation for looking at heat. So you have a lot of combinations. Again, this is what AP likes to do, is put multiple things together. So I have nitric acid and sodium carbonate. So I'm going to write a balanced equation. So I have nitric acid plus sodium carbonate and that yields sodium nitrate, which would be aqueous. Remember, our sodium compounds are always aqueous, plus water plus CO2. And acids are always aqueous. So I'm going to Appendix L to get my values for this. So nitric acid is negative 207.36 kilojoules. Oh, I need to balance the equation too. That's important. So I have 2 sodiums, so I need that 2 there, which is going to give me 2 nitrates, 2 hydrogens. I have 6 plus 3 here, so my 2 nitrates are going to balance, and I really have 3 here, so 1 plus 2 is my 3 for the balanced equation. Sodium carbonate, negative 1130.8 kilojoules. This one's given, it's not in the back of the book, that's why this one I'm giving you. Water, negative 285.83 kilojoules, and CO2, negative 393.509 kilojoules. So I'm going to do heat of reaction from the moles times the products. So I'm going to do 2 moles of NaNO3 over negative 467 kilojoules per mole of NaNO3 plus 1 mole of H2O, negative 285.83 kilojoules per mole plus 1 mole CO2 over negative 393.509 kilojoules per mole. Okay, so that's my products minus the summation of the heats of my reactants, excuse me. So 2 moles of HNO3. 1 mole is negative 207.36, sorry. I was worried about spacing and then totally screwed that up. 207, sorry. Plus 1 mole of sodium carbonate, which is negative 1130.8 kilojoules per mole. Okay, and if you work all of that out, you get negative 68 kilojoules for that reaction. So again, this 467 is eliminating me to the ones place value since we have subtraction. Alright, so now I'm going to go back to all this other data. So just like any other stoichiometry problem, I have to look at how much of this I'm going to be using in terms of moles of sodium carbonate. So that's the next part of this that I'm answering. So I'm going to start with 2.0 times 10 to the 4th gallons of HNO3. And there's a lot of information about that. So there's 4 quarts in a gallon, and 1 liter is 1.057 quarts. So that you would have to be given as well, English to metric. Milliliters to liters. My density, 1.42 grams per cubic centimeter. And out of that grams, 70.0 grams out of every 100 grams. So I'm using this definition of percent. So all of this would be solution. And this is how much is actually the nitric acid. So 1 mole is 63.02 grams, molar mass of nitric acid. And then I'm ready to use the stoichiometry from the balanced equation. So there's 2 moles of HNO3 for every 1 mole of sodium carbonate. So that is going to give me, when you multiply and divide all that through, 6.0 times 10 to the 5th moles of sodium carbonate. Okay. And then I'm going back to my delta H for this reaction and the stoichiometry of this reaction. So for every 1 mole of sodium carbonate from that reaction, I'm getting negative 68 kilojoules of heat. So negative 4.1 times 10 to the 7th, or 41 million kilojoules of heat. That is a lot of heat. So a couple concerns. There's large quantities of oh, I'm sorry, guys. And again, you can just pause this to catch up on all of that. Concerns. So large quantities of CO2, so that can actually cause suffocation. Enough heat. So we based it on water being a liquid, but enough heat to vaporize water and cause steam burns. Okay. Acid is corrosive. Okay. Probably some of the acid is vaporized, so this is not a closed system. So there's a lot of hazards for our cleanup people here. So they would be exposed to acid fumes, large quantities of CO2. So they would definitely need respirators in this one. Could probably even go on to there'd be acid rain formation in the area just because of all of that vapor. So all kinds of problems going on with this. Okay, so again, there's a math problem here, but there are also ramifications for our first responders and people in the area. So they probably had people sheltering in place during that accident and trying to keep windows closed, any kind of air exchange. So if there's ever a situation like this, you'd have to turn your heating or cooling system off because that pulls in air from the outside. So some practical applications of the chemistry. All right, and that is the last problem I have for you for the heat unit.